No physicist can deny that special relativity is based upon a universally constant speed of light. But what if that assumption is incorrect? Hello, my name is Millen Dennis Searle, and I'm a retired high school physics teacher. I have a mathematical alternative to relativity that I've been working on for the past 10 years. I was first introduced to relativity around 52 years ago. This theory that I have is completely mathematical, but it diverges from relativity in that it is exponential in form. It's based upon Hubble's law with a minimum, if not zero, assumptions. All physicists know that light speed is a constant throughout the universe. It is a postulate of special relativity and has been tested many times. Regardless of the motion of the observer, it's always coming in at the same value, about 3 times 10 to the 8th meters per second. Well, Lorentz early on did a calculation based on light speed being constant and varying time to accommodate it. He came out with his famous gamma, the Lorentz factor, which then Albert Einstein used in his special relativity and described the effects of very high velocity as far as time dilation, length contraction, and mass increase. But my question is, what if c, or light speed, is not a constant throughout the universe, but instead is measured as a constant? How can that be? Well, this theory uses Hubble's law to define a exponentially accelerated universe where an observer is accelerating and observing a speed of light that's also accelerating. And it comes in as a constant value. If it's true that light is measured as a constant, then relativity becomes suspect. The model has, in recent times, has run into problems. The expansion at very great distances seems to be accelerating, and as a matter of fact, 95% of the matter and energy in the universe is missing. So they've given a term to it as dark matter and dark energy. Now, the math in my theory is easy if you know how to do it, but it is nothing like relativity, and consequently, it has to be given some time and effort to understand. Basically, the theory that pervades the scientific community now is just using the distance formula and varying time. This theory that I'm proposing has time as an absolute quantity. I am going to show you now how I derived the exponential nature of the universe by starting with Hubble's law. In this graphic, it's shown that starting with Hubble's law, where dr dt is the velocity of a galaxy, and it's equal to some constant times the distance to the galaxy. By cross multiplication, integration, thereafter exponentiation, you can arrive at positions, velocities, and accelerations for galaxies in what we call proper motion. The values there are all given as instantaneous values because, of course, they are expanding and increasing. Attempting to get interest in this theory is very difficult to do. If you have an accelerated universe which is exponential in nature, it will be possible to measure light from one frame of reference to the next frame of reference and get a constant value. What that means is the second postulate of special relativity may be wrong because light is not a constant throughout the universe. In fact, it's accelerating more greatly than the universe itself. And I will show you the math behind that. But if light is not a constant, then all the equations for special relativity and therefore the equations for general relativity are wrong. That's a big statement. But what I'm trying to do in this video is get some attention given to the fact that if you have an accelerating universe, all measurements of the speed of light are constant. I think the main thing that kept going through my mind during creating this theory is that how could it be possible that relativity has been tested so many times and for 100 years, and how could it be possible for exponential expansion to replace it? What happened? And the answer to that I think I found, and I want to show you the essentially the graph of both Lorentz transformation, the gamma, and the e to the h0t of the exponential universe. Here are two graphs. One is for the gamma of Lorentz, and the other is for the expansion factor for exponential expansion of the universe, e to the h0t. They both cross the zero axis at 1, and both have the same relative shape, but not exactly, which makes for a difference in the two theories. Here I have superimposed the Lorentz gamma and the exponential expansion factor. Note the similarity between the two curves. It's close but not exact. As v and t get larger, so does the disparity between the two curves. This disparity is a reason why the Hubble constant is not considered a true constant, which is a mistake. Okay, I want to show now the speed of light when viewed from proper or peculiar frames of reference. First, we have to get our math down for the types of motion. Now we have proper motion, which is dictated by, shouldn't say dictated, but it is given by Hubble's law. That's proper motion. And we will start everything at a point we call, a position we call or zero. Proper motion in a period of time, delta t, and we can call that delta t proper. The reason I say that is because light and peculiar motion have another assigned value, and you'll see why. But proper motion is what we refer to when it comes to the galaxies, the Hubble flow. The farther away a galaxy is, the faster it moves, etc. And I've shown in my videos that the overriding equation for that is dr dt is equal to some constant, which is Hubble's constant, times t. And if you do the math behind that, you'll see that it's a exponential expression, and that expression is this: r, that's the current distance, is equal to some initial distance, and in this case we're going to go r0 here, e to the h0 delta t. In other words, something starts out at r0, it continues on for this length of time, it ends up here, and we could call this r prime. Okay, so r prime is equal to that, and that's the fundamental equation. And if you want to know a distance as opposed to a position, you would subtract r0 from that, and it's e to the h0 delta t minus 1. Gone over all of that. Now, how is light associated with this? Well, the logic that I use, is that if a man's sitting in a chair and he's watching, he turns a light bulb, let's say a flashlight on here, shines it in the direction of motion. As he moves from there to there in delta t, and of course the hard part to believe is that he's moving at the speed of light, he notices that light traveling at the same time will go quite a bit further. If I'm sitting in a chair and I shine a flashlight, that light in 1 second is going to be 186,000 miles away from me. But what the expression turns out to be is the distance that light goes from r0 is equal to, we'll call this r double prime, okay, and we will call that, this is double prime here, that's equal to r0 e to the 2h0 delta t. Now, how did we get that? It's by taking this and taking the assumption that I just told you, and when you do that and you do the math behind it, taking distances involved, you come out with this expression here. Now, to speed things up a little bit, I'm going to show this next graphic, which has all the math you need to show that this is the expression for light. Okay. The math here assumes that light moves at light speed with respect to the Hubble flow, or proper motion. By comparing distances of light and proper motions, it arrives at the exponential expression for light. You may want to stop this video to examine the calculations. Okay, now what is the speed of light from taken from this frame of reference to show how fast light is going relative to this location? In other words, what is the speed of light that light is going? Well, you can just do the differentiation here. However, you've got to realize that light cannot be measured from this position here if it's out here. This has moved on quite a bit of distance. So instead, what has to be done is light has to sample a beam of light, the stream of light, you might say. How fast is light moving at this location? And you see that once you've established that light is moving at a certain speed anywhere, the rest of the universe falls into order. The distance it is from light, from the position that you refer, is going to be different. Every position in the universe will have its own value of light speed. Now, we have established here that light at R0, this, if you put delta t is 0 here and delta t is 0 there, you see that they're both occupying R0. But if you differentiate that, you find a velocity. One is 2r0, 2hr0. The other one is hr0. The thing is that when you measure light, you have to measure where it has been. How fast is it going at the same distance from your reference point R0? Well, how fast is light moving here? To do that, what you have to do is find out how far is this. This is, position is R0 e to the h0 delta t. Now, we put proper here, and we could put proper over here. But the value of light, the value of the speed of light, is not 2ho delta t proper. That delta t proper there is not here. There is some period of time, delta t, we'll call it 1, which is significantly less than delta t proper. Because if we talk about delta t proper, the flow or the observer moves to this position here. But light issuing from the same locations at the same time goes out to here. So what you have to do is figure out how fast was light going as it passed this point. It's sort of like having a river that's accelerating, and how fast is this position relative to the distance upstream? Well, to do that, what we have to do is say, well, this distance is here. What is this distance in terms of light? And that is, and I'm going to put these two things equal to each other. The distance that light goes from here to here is dependent upon delta t here, representing the distance that goes right there. So you would say that the proper distance is r0 e to the h0 delta t proper. Okay, that's going to equal the light distance. The light distance is going to be r0 e to the 2h0 delta t 1, and I'll say that's delta t light. I put 1 here because I'm going to do the same operation for peculiar motion. But let's say this is light, delta t light. In other words, this is the time it takes light to get to the same location as the proper motion does in delta t. This is different than this. This is somewhat less than that. We don't know how less it is, how it relates, but basically the R0s cancel out. Take the log of these, you get h0 delta t proper is equal to 2h0 delta t light. And essentially what you get, if you do the math, delta t of light equals 1/2 delta t proper. Okay, so to reach the same location, delta t takes 1/2 the time that it takes light. And I've discussed before, the important thing of this theory is that time is absolute, and therefore it's more important than figuring out velocities and accelerations. Time is the determining factor in all of these calculations. So delta t light, and you might take this out to the fact that no matter where you are and no matter how you cut it, what's going to happen is that the time it takes in proper motion, light will go twice as far, takes half as long to get to the same location. This is a standard thing between light and proper motion. Well, if that is the case, then we can take this is the distance, so we can try to find out how fast is light moving at this location. Well, going back here to the equation for light, at this location, let's see, where do I want to put this? At that location, we will say that, we will say the velocity of light here, right here, is equal to 2h0r0 e to the 2h0 delta t. That's proper. I put proper there. Yeah. No, well, we're talking here, a 2h0 delta t light. Okay? So the velocity of light here is equal to 2h0r0. Delta t light is 1/2 delta t proper. So it's 1/2 times 2, in other words, e to the h0 delta t proper. Okay, now what's this mean? Here's the velocity of light at this location. I put in that and then changed it to proper time. The proper time that it took light to go there is 1/2 of the time of light. The time of light is 1/2 proper time, I should say. This is the speed here, and the velocity up here of the proper motion h0r0 e to the h0 delta t. That's the flow velocity, or the proper motion, and you'll notice that the velocity of light at the same location is 2h0r0 times e to the delta t proper, and this is 1h. h0 delta t proper. So you see, a person moving in the proper frame of motion looks up and sees light moving away from him at the speed of light with the same expansion factor after it. We have looked at the proper motion versus the speed of light. What about peculiar motion versus the speed of light? Look at this graphic first to understand the properties of peculiar motion. Here we see how the model for peculiar motion works. Simply put, peculiar motion is any motion that is not proper. In other words, it doesn't obey Hubble's law. Because the flow is moving at light speed, it is improbable to assume peculiar motion occurs independent of the flow. It's a combination of a peculiar motion and the flow motion. A proper observer sees a peculiar object moving with respect to him at a velocity somewhat less than light to position RA prime, RA double prime, that is. We can see here essentially the same diagram as before, but instead we have peculiar motion from here to here, which is comprised of proper motion and a peculiar segment, so that someone who is observing from a proper frame of reference sees an object moving, in this case, away from him. And I'll leave it up to you to do the math for if it's coming toward him or whatever. This has to be done separately, and it takes quite a while. But anyway, the peculiar motion is in addition to the proper motion. Proper motion, remember, is moving at the speed of light. Peculiar motion, we can see, this could be an automobile, something of that order, a rocket. Here is light, and we know that's the fastest everything's moving. And you remember that light takes 1/2 the time of proper motion to get to this same location. Remember also that it's like a stream. How fast is light moving here? How fast is it moving there? So what we want to do is the same thing we did before. We want to look at the peculiar motion and write the equation down for the peculiar motion. What's the peculiar distance between here and here? Well, we know it's delta t, and we can call that delta t proper, because you see, in delta t, light moves up to there, proper. In delta t, a proper observer would move from here to here, and in the same delta t, it moves from there to there. So this delta t proper is the length of time it takes a peculiar object to move from here to here. Now, if I write the equation for the distance there, we would say that R peculiar, PEC, is equal to, and that's the R total for peculiar, it's equal to R0 e to the H0 V0 over C0 delta t. And you should see my video series to see why this is true. This here is the constant for either proper motion or peculiar motion. The constant for light now is 2h0, but any fraction of that is part of the time. Okay, so that's this distance from here to here. I didn't write a 1 here. 1 plus. Now you see what that 1 means. It's the proper motion. So if you see, remember, exponents you add, this is R0 e to the H0 delta t times R0 e to the H0 V0 over C0 delta t. So you'll see me make mistakes like that once in a while. This distance is the same as the light distance. We want to find out how fast is peculiar motion moving here, how fast is light moving there, at the same location, at the same instant. Well, that's going to be, for light, we know the equation is R0 e, now we're here, 2h0, and remember this part of it is the multiplier there, the constant for light, 2h0 delta t light. Okay, now what is that delta t light? Is it this? No, that's proper. If it's proper, the light goes out here. Instead, it is the time it takes light to go from here to here. That's delta t light here. If you recall, we used delta t light to go from here to here, and we found it took half the time for light to get to this point, our prime, that it takes to go out there. Now, obviously, this is going to be a little longer. It's going to take light a little longer to get to this location when it lines up with the lead of the peculiar motion. Peculiar motion is the proper plus this little bit. As time goes on, the proper keeps going, the peculiar keeps going. Speed of light, we'll see, is always going to be the same relationship. Okay, doing this, what we'll do is we'll find out how does delta t, this is delta t proper, is it? Delta t proper, yeah, it's from here to here, so it's delta t proper. Okay. How is the speed of light, how is the distance that light goes if the relative to the distance the peculiar motion goes? And what we would do is find out how is the time related to the light time, proper time related to the light time. It is going to be different, obviously, than here. So we do the calculations. Now I saw a little problem here, and what it was that the parentheses shouldn't be around delta t. It's 1 plus v0 over c0 times delta t. So I'll put that like that. And then what I'm going to do is find out how these two times are related, and do that by algebra, basically. What we get is the log of this is equal to the log of that. And it comes out to be 1 plus v0 over c0 times delta t proper is equal to, now the R zeros canceled out. The 8 that we took the log of this, so h0 delta t equals 2h0 there. So it's equals to 2h0, but we canceled them out. I canceled it out here. 2 delta t light, and therefore divide both sides by delta t, and I'll just do what I do, and what I get is this thing. So it takes light to get to this location here this amount of time. It's 1/2 of the value there. So what's that mean? Well, how fast is this object moving here? VR peculiar is the derivative of the expression for R peculiar. It's this part right here. So if I take the derivative of that, it's HO R0 E to the HO times 1 plus V0 over C0 delta T proper. Okay, now this light thing here, this light expression, we're going to differentiate that to find the speed of light, but then we're still in light time, and we know that there's a relationship there. I'm going to put up here, I'm going to say VR light is equal to the differential of this HOR, no, it's 2 HOR 0 E to the 2 HO delta t light. So you see the same thing's happening for this. And what I see here is if I plug this in to there, the 2's cancel out and I get VR light is equal to, the 2's cancel out, 2HOR 0 E to the 2HO, I'm sorry, E to the 2HO, and I'm going to cancel it out. After this is delta T light, I'm going to change it to proper. So times 1 plus V0 over C0. Very sloppy here. Delta T proper, I'm getting it into proper time. Okay, divided by 2. Okay, so I cancel the 2's. Okay, I'll take that out of there. 2, 2. Okay. So what do I get? What do I get? I get that light is once again, I'm getting that it's seeing that the subtraction of this from this comes out to be this value here. And it has the same expansion factor after it. So you can do that. How will a peculiar observer see light moving? It'll see it moving at HOR and then the expansion factor, but it has the same expansion factor. So it's going to see it as moving HOR0, and we know that even Hubble said this. And you can straighten that out. It's not, the time is not exponential form. Okay, so both proper motion and peculiar motion come out with the same result. The speed of light is going to be determined by the person, the observer, either in the proper frame of reference or the peculiar frame of reference, because they both have the same expansion factor after it, and it will be determined to be HOR0. It's the speed of light, regardless of the motion of the observer. Now, I haven't done anything in other directions. Everything's happening it's expanding in all directions. So this works in all directions, but you can set up positives and negatives, and it always works out mathematically. This is a good argument for considering the universal exponential expansion model for the universe, because light is always measured as a constant, even though it's accelerating.